So I now want to say just a few words about big O notation. This won't play a big part in the first half of the course. It's only in the last chapter on Taylor expansions and Taylor polynomials where we will really care about this. But let's write down the definition. And I'm trying to keep the definition slightly simple here, which can make it awkward to use actually, but I'll try to formulate it in a simple way. So we write an is equal to the big O of Bn if there exists a constant c such that an in absolute value is less than or equal to c times bn in absolute value for every n bigger than 1 or well, wherever these guys are defined. And you can say, so this is me trying to write this in a simple way. And really, if you want to do it more generally or as it should be, then you should say if there exists a c and an n such that this happens for every n starting at capital N. Point is, we don't really care if this inequality doesn't hold for the first 100 or 1,000 entries, as long as it holds at some point. And here we would also put as n goes to infinity. So the reason why I don't really care about this now, or I really try not to emphasize that now, is because it won't matter to us. It won't matter to us in the examples we look at. So I'm trying to basically give you a baby version of this definition. In the end of the course, we'll have the proper one. In any case, so how does this look? Well, so usually we think of Bn as being positive. So by the definition, they don't have to. But if the Bn's are positive, we can take away this. And if we want to take an example, we could put, I don't know, the Bn's equal to 1 over n. So then we would have here 1, 2, 3, etc. And then we would have the value 1, a half, a third. So then this inequality here would say that the an's are less than a constant times 1 over n. And this constant, well, maybe it's 2. So an is bigger than 2 divided by n. Maybe it's 1,000. So maybe an is smaller than 1,000 divided by n. Or maybe it's 1. Who cares? The point is that an is now squeezed under this guy, right? And we can open up this inequality here to get here an less than or equal to c divided by n and bigger than minus c divided by n. So here we can also put this negative sequence like this. And then somewhere inside of this envelope given like this, my sequence an has to exist. And of course, having such an inequality, it follows here that if n goes to infinity, well, this goes to 0, this goes to 0. So by the squeeze, this goes to 0 as well. So as soon as this bn goes to 0, then the big O notation is a very quick way of telling you that this goes to 0 as well. Or if this is less than n squared, then you know that, well, this guy is bounded above and below by n squared, so plus minus n squared. So if I divide this by n to the third, then an divided by n to the third will go to 0 as well, and so forth. So this is a very efficient way of telling us about the growth of this guy in a way that's suitable for algebraic manipulations. For instance, if I want to take another example, then I know that sinus n is less than 1 and bigger than minus 1. So this means I know that sinus n is less than 1 in absolute value. So I know that sinus n is equal to big O of 1. But this means that sinus n divided by n is equal to, well, notice here, if I divide by n everywhere, these guys are also divided by n. So when you're used to working with a big O, you know that you can just throw this guy on the inside here. And then you know this guy tends to 0 as n goes to infinity. And this would be another way of expressing the squeeze theorem. And this is something we'll look more at, as I said, at the end of this course. So here, you're just getting a sneak peek at this.